Hello there, students. In this video, we're going to learn about average acceleration. Acceleration describes how quickly your velocity is changing and is defined as the change in velocity divided by the change in time, and as an equation reads a bar equals delta v divided by delta t. Because velocity is a vector, so too is acceleration. This means an acceleration can happen if you change either of the vector properties of velocity, meaning you can change its magnitude by speeding up or down, or you change its direction, or both. Starting from rest, or an initial velocity v0 of 0 meters per second, a Formula 1 race car can accelerate to a speed of about 30 meters per second, which is about 67 miles per hour, in 2 seconds. Let's find out what kind of acceleration that is. Given our initial and final velocities, and the time it takes, we can plug these into our equation for an average acceleration. We find that the average acceleration of the race car is about 15 meters per second squared. Now don't let that small number fool you. The acceleration of Earth's gravity is just a mere 9.81 meters per second squared. That means if a Formula 1 race car could drive straight vertically away from the surface of the Earth, it could escape our planet's gravity. Let's consider another example now. If you're fully stopped at a red light in your car, then accelerate when the light turns green, we can start the clock at t0 equals 0 seconds when the light turns green, and your velocity is still 0. After 10 seconds, you reach your cruising speed of 40 miles per hour, which is about 18 meters per second. You cruise along for about 20 seconds until you start slowing down for the next red light. It takes you about 5 seconds to slow all the way back down to a stop. We can now calculate the average accelerations of any part of the trip. Let's start with the entire trip. Our final velocity at the end, v3, stopped at the red light, is 0 meters per second. Our initial velocity stopped at a red light, v0, is also 0 meters per second. So our average acceleration was 0 meters per second squared for the entire 35-second trip. We can also look at the average acceleration of just the first leg of the trip, starting from rest and accelerating to the cruising speed. Then, our initial velocity stopped at the red light is 0 meters per second, and our cruising speed of 18 meters per second is the final velocity. From t0 to t1, or the time it takes to make this change in velocity, is 10 seconds. Putting this all together into our equation for average acceleration, we get 1.8 meters per second squared. Finally, let's calculate the average acceleration from the time you first reach cruising speed to stopping at that next red light. In this case, your initial velocity is the cruising speed of 18 meters per second, and your final velocity stopped at the light is 0 meters per second. The change in time from the moment you reach 18 meters per second to the moment you stop is a total travel time of delta t equals 25 seconds. Which we get from t3 minus t1. Putting this into our equation, we find an average acceleration of negative 0.72 meters per second squared. We can also see how this might look on other graphs. We can look at all kinds of graphs, but the most important are going to be the position versus time graph, the velocity versus time graph, which we just used in examples, and the acceleration versus time graph. We started from rest with position x equals 0 meters, velocity equals 0 meters per second, and acceleration equals 0 meters per second squared. Then, we accelerated at a constant rate, which means our velocity increased at a constant linear rate, and our position increased, simply meaning we made our way down the road. Eventually, we make it to our cruising velocity, so we stop accelerating, meaning our acceleration drops to 0. Our velocity is then unchanging, so it is just a constant value, and our position still increases, since our velocity is a positive value even if it is just a constant. Then, we slowed down for the red light, so our acceleration was negative, our velocity decreased, but because our velocity still had a positive magnitude, our position still increases. But it doesn't increase as fast. In fact, its rate of increase also slows related to how our velocity slows. In that last segment of travel, as we saw in our example and in the graph, we had a negative acceleration because we've chosen a coordinate system such that the direction of motion, or velocity, is in the positive coordinate direction. and when we are slowing down, our acceleration has to go in the opposite direction of our motion or velocity. There is often some confusion between the terms negative acceleration and deceleration. What it comes down to is keeping track of your coordinate system's positive direction and the direction of motion or velocity. Deceleration is an acceleration that is always in the opposite direction to your velocity, regardless of your coordinate system. A positive acceleration is any acceleration in the positive coordinate direction. And a negative acceleration is an acceleration in the negative coordinate direction, which is entirely dependent on your choice of coordinate system. Let's use this positive direction to the right for our coordinate system. Then, here are some quick diagrams of some scenarios illustrating positive and negative acceleration and decelerations. Pause the video here and take a quick moment to see if you can figure out which ones are positive or negative accelerations or decelerations. Here are the correct answers. Leave a comment below if you have a question about why one is such. Now, if you recall from our previous video on velocity, we saw that the slope of the line connecting 2 points on a position versus time graph gave us the average velocity. We can also take the slope of the line connecting 2 points on a velocity versus time graph to get an average acceleration. For example, if we look at the beginning and end of the cruising velocity, where we know we had zero acceleration, we can see the slope of this line is flat, and the value of our acceleration on the acceleration versus time graph is 0 for that period of time, as we should expect for our velocity with zero slope. The connection between position, velocity, and acceleration is fundamental to kinematics, and we'll start tying them together in the next video. Thanks for watching and learning about physics. If you have any questions, please post a comment on the video or on my Facebook page in the video description.